thermal conductivity and resistivity of soil materials using the TLS 100. My name is Jolie McGrath, the Distribution Coordinator at ThermTest, and I will be the host for this webinar. Before we begin, I'd like to mention our upcoming 3 webinars that will be presented this winter. All attendees to this webinar will receive an email invitation for our upcoming webinars once registration is open. Our Q&A session will be held at the end of the webinar, where Dr. Daniel Cederkrantz will answer questions with the remaining time. If you would like to ask a question, we encourage you to type it in at any time during the webinar. If we run out of time during the Q&A, all remaining questions will be answered in the post-webinar email on Friday, November 13th, and include a link with the recording. Our speaker for today is Dr. Daniel Cederkrantz, CEO of ThermTest Europe AB. Before his role with ThermTest, Dr. Cederkrantz studied at Chalmers University of Technology in Sweden, where he received a PhD in material science with a focus on thermoelectric materials. So, I will pass along this to Dr. Daniel Cederkrantz.
Thank you, Jolie, and welcome everyone to today's little webinar. Here's a brief agenda of what we're going to talk to. So we will start with introducing the samples that we will be looking at. We will discuss the advantages of the transient line source method and the specifications of our TLS 100. There will be a brief look at the theory about the testing method, and we will look at a few other methods that might be options for testing the sample types that we are looking at today. Then we come into the part where we look at the TLS 100 for testing hard samples like concrete and so on, as we will see very soon. There will be a testing demonstration. We will see the results that come from these tests, and of course we end up with a summary, and then we move on to the Q&A session, where we hope for nice questions from you all. So today's samples that we will look at is concrete and polycarbonate. Of course, concrete is the most typical example of samples that you would, hard samples that you would test with the TLS 100. It is not the primary sample for the TLS 100, which would be soil, but concrete is maybe the secondary sample and also a very, very important application for the instrument. Concrete varies very much depending on density, aggregates inside it, moisture levels, and other additives. So it can be very important to test the thermal conductivity of concretes, where this number is valuable in building and constructions. Polycarbonate, on the other hand, is a more well-defined material, if you want, but it's a very nice demonstration sample, being transparent and homogeneous and so on. So we will take a look at also that. So first a look at the star of this presentation, which is the TLS 100 instrument. And you can see it here to the left. And for you who have seen this machine before, this is the updated version that will soon be available, now with a nice color screen. The instrument is, of course, as mentioned here already, designed for testing soil, rock, concrete, and polymers. So quite wide range of samples, with a conductivity range from 0.1 up to 5 watts per meter Kelvin, which is a fairly wide range from not really insulating materials, but just above that, and up to moderately conducting samples. It's a pretty fast machine. A test time is 3 to 5 minutes, depending on the probe that you're using. It's accurate, within 5% normally, and reproducibility of 2% is from test to test on the same sample. So pretty strong. You can use it in a pretty wide temperature range, from -40 degrees up to 100 degrees. The machine itself will not control the temperature, but this is the environmental range that the probe will operate. Sample size that you can work with depend on the needle. Of course, it needs to be as long as your needle at least. So depending on the needle you want to use, 50, 100, and 150 millimeters long, while the diameter of a sample should always be at least 50 millimeters. You can always test a bigger sample. That is no limitation in sample size. So of course it can be used in situ. You can go out and test soil in a trench, and therefore, of course, sample size is unlimited. It follows 2 standards, fully complies with 2 standards. From the introduction of the 150 millimeter needle. So the traditional standard we have been using is ASTM D5334. Now we also fully comply with IEEE 442 2017, which is very nice to be able to add to this. The TLS comes as a complete kit. When you complete kit when you buy it, it's delivered in a waterproof and portable case where you can store all your accessories like thermal paste, a poker to make a hole in the sample if it's soft, sleeves for casting samples, which we will come back to in a while here. You will get a verification sample to check the calibration of the machine. You will get drill bits to drill holes in harder samples, and of course it comes complete with batteries. So once you get it, you can get out testing immediately. So something about the advantages of the method. Well, first of all, the method is standardized. So as mentioned, there are now 2 standards that apply, which is very nice. So you can select the one that's most applicable to your area of testing. It's very easy to use. Normally there is no or very little training required to start using it. If you follow the manual, you will be able to test without any big errors. It is fast, and you will get the results in just a few minutes, as long as this temperature of your sample is stable before testing. You get the results directly. You don't have to make any calculations by hand. On the screen of the device, you will get your results immediately after testing. And the results are also automatically saved to your device, so there's no big risk of losing the data if you didn't take notes. It comes nicely factory calibrated, so you won't have to do recalibration. You get the verification sample, so you can make sure that your calibration is valid, but you don't need to do yearly or monthly recalibrations like you have to do for certain other instruments. You can quickly swap the probes, especially with this new design that you saw in the picture here before. You don't have to do anything else than basically unplug and replug a new needle, and the instrument will be ready to go for testing with that instead. I would also say it's a very affordable method. It's probably one of the least expensive thermoconductivity methods on the market, even if you could compare it with similar type devices. And you will get all you need in a single portable case. So all you need comes in the kit, and you can start testing immediately. So let's move into the more nitty and gritty stuff. Let's look at some theory here. So some important things with testing with any transient method, I should say, really, is that before you start testing, we need to have a sample where the temperature is at equilibrium. We cannot have a shifting temperature inside the sample when we want to do a test. So you cannot bring a sample from outside into your lab and start testing immediately. You need to wait for a uniform temperature inside your sample. What we do with the probe, the needle that you have seen in these pictures, is that we heat it up. So there's a heating element inside the needle, and it starts heating up during the measurement, and we record the temperature increase with a thermocouple that's placed inside the needle in the central part of it. We can then plot the temperature rise against time, or rather the logarithm of time, and that should turn out to be like these curves that you see down here, where we have an initial part that we have to remove, because in the beginning, when we start heating, we will see contact resistance between the needle and the sample. We are not interested in that, so since it's a transient method, we're allowed to remove that. Then we come into a linear, steady-state part of the curve. This is what we use. The thermoconductivity will be inversely proportional to the slope of this part of the curve. And you can also get the thermal resistance of your sample, which is very similar or very basic, because it's really the thermoconductivity and the inverse of that. So it's just 1 over thermoconductivity, and you have your thermal resistance. And you have the most fundamental equations down here, where basically you can see from the slope, and with knowledge of your heating power, we can find the thermoconductivity. Of course, there's calibration involved also here, but that's something we don't have to go into the details of. So something about a few other methods for thermoconductivity testing, because there are many ways to test thermoconductivity. Not all of them are suitable for testing hard samples, as we talk about here today with concrete and so on, but there are, of course, many methods that could be applied here. For thermoconductivity testing, we have 2 main types of measurements. We have steady state and we have transient. The steady state methods are traditional methods. You find heat flow meters here, guarded heat flow meters. guarded hot plate, and there's something called a hot box. These test thermoconductivity in a single direction under steady state conditions. So they require comparatively large samples for most of the time. It takes time to do the testing, and it's certainly not portable. So these are in lab for very careful and accurate research. Those machines are excellent, of course, and the standard of thermoconductivity testing. But transient methods have very nice applications because they are flexible and fast machines. You have the transient plane source, which is a very versatile instrument, do everything from insulation to conducting metals. But it's an expensive material and it is not very portable at all. We have the laser flash method. It's fantastically for testing dense material up to very high temperature. Of course, expensive and not something that you bring to the field. And then we have the transient line source, which is designed for a more narrow field, but it comes at a very nice price compared to any of these other methods that's been mentioned here. So that being said, let's take a look at how to use this instrument. So for testing hard samples, which is the focus of today, we normally use our 50 millimeter needle, the smallest needle, but it's the shortest needle, I should say, because it also has the largest diameter of our needles. It's 4 millimeter in diameter, which will really help you during this testing of hard samples. So before you start testing, you should always study the manual and perhaps also the relevant standards, because in the standards you can get information on how to prepare your samples correctly in accordance to that standard. But for the testing itself, you need to have a minimum 50 millimeter diameter sample and 50 millimeter length, as discussed before. We need to drill a hole in the center of this sample, as you see in the picture down here or up here. We need to drill in the center because we want the same distance to the outer boundaries from the needle at all times. The hole should be at least 55 millimeters deep. So this is, as you see, a little bit more than the 50 millimeter minimum length. Often the samples are probably larger than 50 millimeter long. And you should drill a bit further than the length of the needle, simply because you will have to use contact paste. And some of the excess contact paste might end up at the bottom of the hole and you don't get the needle all the way down, which is bad. If you have a little bit extra space, you will not run into problem with this. If you have a 50 millimeter long sample, drill through it so you can push out the extra contact paste. Once you have your nice hole prepared, you cover it with contact paste and make sure that the entire needle goes into the sample. That's very important. You can't have part of the needle exposed. It should look like the picture down here, where the needle, where the handle of the needle is in perfect contact here with the sample, to make sure that there is no issues with with heat losses from the needle itself to surroundings. Once you have the needle in, we can start up the instrument, make sure that the correct sensor is selected. If relevant with a new design, you don't have to worry too much about that. Check your battery status so you don't run out of battery during testing, of course. Once that's done, take a look at the temperature, because the machine will continuously monitor the temperature of the probe. And now your probe is inside the sample. So that means that we measure the temperature inside the sample. Need to make sure that this temperature is stable, as we have already discussed. Sometimes you have to wait a little bit. I would suggest maybe waiting 10-15 minutes, especially if the hole is a tight fit for the needle. You can actually generate some heat just through the when pushing the needle in. So make sure that the temperature is allowed to even out. That's from friction then. Now you're ready to test. You name your sample, and then you can run manual test just by pushing the blue button you see here on the picture. Or you can set it up to do multiple tests in an automatic mode. That's a nice way to get some statistics, and the machine will take care of that while you do other work, for instance. Once you're done, pull out the sensor, clean it, and return it to its protective sleeve and place it in the case, of course, to avoid any damage. And you don't want to leave the paste on the needle also, since it dries up and you might have issues getting rid of it later on. And now we will have a look at a little video, which I think Jolie will help me start here, showing the procedure. So you start by marking the spot and you drill your hole. using normally a hammer drill, I would guess, to make this process a little bit faster. Now we have fast forward, which helps, of course. So all the way down with this drill bit to have this little extra depth of the hole. So the entire needle and then some can fit. With the hole ready, get rid of the dust and drill it out carefully. So because you don't want the dust sitting in the hole and blocking the needle once you want to get it inside. Try to put your needle in dry first to make sure it fits. Otherwise you have to get back to your drill. Apply the grease or the contact paste to your needle. There is no specific amount you need, but make sure it's enough to cover the needle once you input it, and you twist it around to make sure it covers nicely and you ensure good contact. Now you're ready to test. The sample is named here, concrete, and we do the test. What it does now in the beginning, it checks for drift, as it says. That's basically monitors that the sample temperature is stable, and you can actually get a warning if temperature of the sample is shifting too fast. After that, it moves on to the heating cycle, where we heat up the probe, and you see the transient here. This is not logarithmic time. Then you also get a cooling cycle, where the probe is cooling down, and results follow. And then we got a little sneak peek of what we will look at soon. Results pops out, and here you see 3 repeated tests of this piece of concrete. And at the bottom, you get the average thermal conductivity, which you find here. So about 1.7, typical thermal conductivity of a piece of concrete with a very small standard deviation. So you see here the standard deviation is less than 1%, which is what we should expect. And it's also nice to see that it is fairly easy to just do this test and get this small variation in the results. So as you see, it's not very hard to use this device for the testing. And this is how you test concrete. You can drill as many holes as you need and just repeat your testing from sample to sample, and you can create statistics like this. So try to make more than one test in each sample to be able to get this statistics and get the standard deviation for your graphs or for your reports later on. As an alternative then to using this rugged 50mm needle as we have seen now, you can actually use the default needles that comes along with the instrument, which is the 100mm needle. It's very hard to drill a hole for this needle in a concrete sample. Since it's 100mm long, only 2mm in diameter, it is really, really tough to drill a suitable hole without breaking the drill bit. So instead of trying that, you can use sleeves. So this works very nicely if you have samples that will be cast. So if you have a concrete sample and you are a producer or your builder, when you cast the concrete into the container or the place where you want to use it, you can put a metallic sleeve in the still soft sample and let it sit there while the material hardens. And that means that you have a perfect hole already fitted in your sample once it's hard, where you can push this needle in and you can run your test. This is also a way to test the sample during the curing process, for instance, if that's of interest. And you can use this for any kind of sample that's really can be cast. So it can be concrete, it could be a polymer or any other solidifying sample. And we will see a little video here how this looks. So I allow Jolie to start that one. It's very similar, of course, as before. You cover the needle, and in this case, then it's much longer, and it has to go into this quite small hole, but it needs to go all the way in. Also here, you need to use your contact paste. We can also use the 100mm needle for testing other types of dense solid samples, but they need to be a bit soft, because then you're actually able to drill this 2mm diameter hole. Now we need to have a longer sample, 100mm long, the diameter still 50mm, and then you can use the 100mm needle. Still requires the use of the contact paste, and you follow basically the same procedure as we discussed before for the 50mm needle. Suitable samples for this can be polymers. I've seen it used for dense clays, where you cannot really push the needle in. You have to drill first. Then it works nicely with a 100mm needle, because the sample will give to the drill bit without heating up too much and breaking the needle. Oh, sorry, the drill bit. So it's a limited type of material with this use, but it works nicely where you can make this 2 millimeter hole. And we will see how this looks in the polycarbonate, which is a nice example because it's transparent, so you will be able to see how the needle goes in. Normally there should be contact paste here, but to be able to better see how the needle penetrates here, there is no paste at this time. But you see, it needs to be a snug hole, and it's not a big hole, so take care when you drill this, because it's very tedious when the drill bit will break. So results then from testing polycarbonate. As you see, this is quite a much more insulating sample as compared to the concrete we looked at before. The sample here is Lexane, which is a trade name for a polycarbonate. Thermoconductivity, you can see the average value down here. It's something like 0.28 if you round it a bit. And standard deviation for this testing is very small, so it's a very good test. And accuracy, this is as compared to the literature data. And you see here the results as measured with the TLS 100 are roughly 1% off only from literature data, which I would say is very good for this little machine to perform so well on a polymer sample like this. So what can we do then when we have the results? We need to be able to view them and do something with them, of course. So the results are displayed on screen, as mentioned before. You can also browse the previous results, and you see here a screenshot of the new color screen, where it's very clear and easy to read. You see there in the top corner, it also measures the temperature, so you can keep an eye on that all the time. You see here at the top which type of probe you have used. So this is the 50 millimeter probe, and here's thermoconductivity, watts per meter Kelvin, and thermal resistance, which is the inverse, meter Kelvin per watts. And you name your sample down here, and it's a one button to start. Once you have a bunch of results, you can easily export it to Excel directly from the TLS 100, where everything is stored on a micro SD card, so you can store thousands of tests on it. So usually a good idea to every now and then do a transfer of your results over to Excel to be able to deal with them more easily. We will also soon be launching a companion app for the instrument, where you can view the data by connecting the instrument to a PC where you have the companion app, and we'll make it quite easy to browse your data, remove data from the machine, and view the transients and so on, and further transfer the data to Excel perhaps if you want to use it there instead. And that brings us to the summary of this little presentation, where we can conclude that the TLS is a very popular instrument for in situ and laboratory testing both. For any type of sample that we have discussed now, we have discussed mostly the hard samples, but of course it's also very commonly used for soil, as mentioned in the beginning. So soil, rock, concrete, asphalt, polymers, those are probably the main areas. Follows two standards. It's a very affordable instrument. It's also very popular, as mentioned before. There are hundreds of TLS 100 units across the world right now, so it's made an impact in the field of thermoconductivity testing. And since it's very easy to use, it doesn't require you to spend a lot of time on training and practice. You can just move ahead with testing as soon as you receive the machine. And with that, I would like to say thank you to everyone, and please shoot your questions over if you want, and I will give the word to Jolie for reminding you of our upcoming webinars.
Thank you, Daniel. Just a reminder, we have these 3 webinars coming up this winter. If you'd like to register, you'll get access to that via email shortly once that is open, or you can go on the website at any time to register as well. So we will just wait for a few moments until people have a chance to type in their questions. And until then, I'll just be on mute.
So we have a little question in here about if we can use the machine to test coarse granulate materials like crushed stone. I would say this depends on the size of the particles. if you crush this stone down to maybe 5mm pieces or something like that, it should probably work. You should then use as long needle as possible to get a better average of the material. I would not use this small short needle. Instead, you need to use a long one because that covers a bigger volume of this material and gives you an average that will be more reliable. But it is trickier to work with these very large particle samples. If it would be mixed up with smaller particles, like more like sand, with bigger particles, it's less of an issue. But you don't want to have a too big fraction of air because that makes it complicated. Yes. Well, it seems like we have been fairly clear during the presentation. I think Julie will agree that if you have any more questions coming in, you're also, of course, welcome to send them with an email to us, and we will get back to you with a reply.
In the chat box, anyone can write it down if they'd like to ask questions in the future. And then we will end this webinar. Thank you all for attending.
Yep. Thank you very much, everyone.